The third example in the plane area series involves cosine x, sine of 2x, and the x-axis. Check how the area is solved here in integral calculus. The problem for this example involves three functions: the trigonometric curves of cosine x and sine of 2x, and the line when y is equal to 0. The curves come from the trigonometric functions cosine x and sine of 2x. Then there is a third function of a line at y equal to 0. Even with the line involved, the plane to use has its x-axis in terms of radians, and the y-coordinates are still in whole numbers. The initial steps to sketch the curves, including the line y is equal to 0. And the first method we use is tabular substitution of x. Start off with the function y as cosine of x. So at x equal to 0, y is cosine of 0, which is 1. When x is pi over 4, y is cosine of pi over 4, giving root of 2 upon 2, or 0.707. Next is when x is pi over 2. Y comes out as cosine of pi over 2, and that is 0. Then, there is x as 3/4 of pi, making y as cosine of 3/4 pi, which is simplified as negative root of 2 over 2, or in decimals, we get negative 0.707. Then, when x is pi, y is cosine of pi, which is negative 1. Do the same substitution for the second function, when y is sine of 2x. So at x equal to 0, sine of twice of 0 is 0. When x is 1/4 of pi, y becomes twice of pi over 4, and that is 1. Then, when x is half of pi, y is sine of 2 times pi over 2, or simply pi. And its sign makes y 0. When x is 3/4 of pi, y is sine of 2 times 3 pi over 4, or that is negative 1. Then when x is pi, sine of twice of pi is 0. So from the illustration, look for the area bounded by the three functions considering the first curves, and note that the limits of x are somehow at half of pi. A shorter way to trace the curves is by analyzing the function's period from the equation y is equal to a times sine of the quantity b times x minus h plus k. A is the coefficient of sine, which gives the amplitude of the wave. H is the horizontal movement of the wave from the origin, and k is also the vertical movement of the wave from the origin. Period is then solved from 2 pi over b, where b is the coefficient of x from the equation. Start with the first function y as cosine of x. Having 1 as the coefficient of x, we note that the period is 2 pi over 1, or simply 2 pi, and cosine starts at 1. So the whole wavelength is 2 pi, and the first curve covers 0 to pi. The second function of y as sine of 2x has a period of 2 pi over 2, giving pi. Sine also starts at the origin. So the first hump of the sine curve has limits from 0 to half of pi. The next step is to identify the differential strip suitable for the circumstance. Remember that the strip should touch two different functions. So in case we start with a horizontal strip, one would notice that the ends of each strip touch the red and yellow curves. When we use vertical strips, the ends would touch a curve and the x-axis. Let's go with the horizontal elements. Now move on to determining the limits, or the extreme points for the area. Since we opted to use horizontal strips, the limits would start from y as 0 to the intersection of the curves. What we usually do is to equate the equations, that is, x in terms of functions 1 and 2. So let's transform each function to extract x. With y as cosine of x is arc cosine of y. And also, from the second function, y as sine of 2x is arc sine of y. Then x is computed as arc sine of y over 2. Equate the two x's and have arc cosine of y is equal to arc sine of y over 2. However, it seems difficult to solve for y when inverse functions are involved. So let us check our luck when using vertical elements. Using vertical elements, the ends touch a curve and the x-axis. So there would be a change as the functions deviate. And what we are going to do is to divide the area into two. One is when the upper y touches the red curve, and the other is under the yellow curve. Having two areas requires the location when to change integrals, and that would be determined by figuring out the intersection of the two curves. Now equate the functions y as equal to y, which is cosine x as equal to sine of 2x. With an angle of 2x, simplify the function using double angle identities, making the equation cosine of x is equal to twice of sine x cosine x. At this point, there are two methods to look for the intersection. One is by dividing the equation by cosine of x, resulting to 2 sine of x as equal to 1. Simplify the equation further into sine of x as 1/2, or that makes x as arc cosine of 1/2, which is a sixth of pi. The other method of simplifying the equation right after equating the two curves is by transposing cosine x to the rest of the equation, so the result is 2 sine of x cosine x minus cosine of x is equal to 0. Extract cosine of x and have cosine of x times the quantity of twice of sine of x minus 1, and this is equal to 0. Then apply zero property and equate the first term, cosine of x, to 0. X is then arc cosine of 0, which gives x as half of pi. The other term is also equated to 0 to have 2 sine of x minus 1 as equal to 0. Transpose 1 to the other side and divide everything by 2, so x is arc sine of 1/2, which makes x as a sixth of pi. The fourth step is to generate the integrals. Since we reverted back to vertical strips, the differential area of each strip, which is length by width, becomes y times dx. Y is again taken per coordinate, that is y upper minus y lower. And again, although we are working on just one solid area, the difference in curves would require the area to be divided into two. So we have the total area as the summation of A1 and A2. Now we figure out the integrals of each. Area 1 works with the red curve on top, so the formula is sine of 2x minus 0, that is, x-axis times dx. The limits are from 0 to pi over 6. The second area has the same concept, so the integral is cosine of x minus 0 times dx, with limits from a 6 of pi to half of pi. The last step is to integrate each equation starting with area 1. As was identified earlier, the differential of area 1 is equal to sine of 2x minus 0 times dx. The limits are from 0 to pi over 6. Simplify the integrand and have area 1 as equal to the integral of sine of 2x dx from pi over 6 to 0. Analyze the integral. U is 2x, and its derivative is twice of dx. This entails that we are to adjust the integral by multiplying 2 to the derivative and also balancing the factor by multiplying 1/2 before the integrand. Then integrate the function to come up with negative half of cosine of 2x from the limits pi over 6 to 0. Next is to plug in the limits and come up with negative half of cosine of twice of pi over 6 minus cosine of twice of 0. Cosine of 0 is 1, and cosine of pi over 3 is 1/2. So the area becomes negative 1/2 times negative 1/2, which becomes 1/4. The second area has the equation of derivative of area 2 as equal to cosine of x minus 0 times dx. Integrate both sides from half of pi to pi over 6 to take area 2. The formula is then simplified as area 2, which is equal to the integral of cosine of x times dx from half of pi to pi over 6. Again, analyze the function and have u as x. Then its derivative is dx. So area 2 becomes sine of 2x from half of pi to pi over 6. Then place these limits into action and make the expression sine of twice of pi over 2 minus sine of twice of pi over 6. This can be reduced into sine of pi minus sine of pi over 3. Sine of pi is 0, and sine of pi over 3 is root of 3 over 2. So area 2 becomes negative root of 3 over 2. Although the answer turned out as negative, take the absolute value as we are computing for an area. Area 2 is then root of 3 over 2. Lastly, the total area as area 1 plus area 2 can be written as 1/4 plus root of 3 over 2, which is simplified as 1 plus 2 root of 3 over 4. In decimals, we have 1.1160 square units.